Section 3.3, we were working in this section last time and we had covered the multiplication part of the whole numbers here. And today we're going to do the part about division. So the first thing we're going to look at is a definition of division. This definition of division feels a lot like the definition of subtraction as it related to addition. For any whole numbers a and b, as long as b is not 0, a divided by b equals c. If and only if c is the unique whole number such that b times c is equal to a. A is called the dividend, b is called the divisor, and c is called the quotient. Okay, so this says, just notationally, a divided by b is equal to c. So I'm going to take that with some numbers so that we can make sense of that. 6 divided by 2, and we know that that's equal to 3. And the reason we know that that's equal to 3 is because 2 times 3 is equal to 6. That's the way that the definition phrases it, with numbers in it instead of with variables. Okay? And again, it's the same thing that happens after you learn multiplication and you're learning division as what happened when you're learning subtraction after learning addition. If you already know that 2 times 3 is 6, I should be able to say, I have 6. How many 2's do I need to make 6? Well, I need 3 of them, because I know that 2 times 3 is 6, and so forth. Okay, we have 4 models for division. One of them is a variation of the other one, and so your book doesn't identify them as being separate, but I want to show you the 2 variations. The first one is a set partition model. And this is Junie. She has 24 rocks, and she wants to give them to 6 of her friends. How many rocks will each friend get? So what we're going to do is we're going to sort of identify that she has 6 friends here, and I'll draw that with a box, I guess. So here's friend 1, friend 2, friend 3, kind of like placemats at the dining room table or something. Here's our 6 friends. And we've got to evenly divide the 24 rocks among those groupings of friends, those individual friends. So maybe she decides to do one at a time, and she puts 1 rock in each person's pile. Maybe she decides to put a couple of rocks in each person's pile, but at some point she ends up putting how many rocks in each person's pile? 4. Okay. So in this variation, we have the rocks and we know how many people need to get them. Right? We know how many groups of them we're going to have at the end of the process. That's actually quite different than the next one. Junie has 24 rocks, but she bags them together in groups of 6. If she gives one bag to each friend, how many friends will receive a bag of rocks? The difference is, this time, she doesn't know how many friends, she knows how many groups of rocks, or how many rocks are going to be in each group, right? Instead of trying to figure out how many rocks do I put in each rectangle, because even as you did it, and as I did it, I said, maybe she starts out with 1 person, and then she says, oh, you know, one rock per person, and she's like, oh, I have a whole bunch more, maybe you each get 2, and then she realizes at the end they each get 4, right? The question is, how many rocks does each friend get? Here, the question is, how many friends actually get the rocks? Because she's divvied them up beforehand. So she's created 6 in a group, right? Groups of 6. So here's one group of rocks. Here's the second group of rocks. I'll go back and put the answer on the other one. I just realized I didn't do that. And here's the third group of rocks. I need one more. Where am I going to put it? Let me move this one over. All right. So we have 1, 2, 3, 4 groups of 6 rocks in this example. So the answer to this question was actually 4 friends, whereas the answer over here was that they each got 4 rocks. It's the unknown quantity that's different. Now, let me give you a very good example of where you've seen these variations used. And the example is actually in a classroom. So if a teacher wants to randomly choose groups in a classroom, there's a couple of things she could decide. She could decide, I want to make sure that I only have 2 people or 3 people or 5 people or whatever per group, right? I want to make sure I only have groups of a certain size, okay? That's this example. The groups are a certain size. And the way you get that to happen in a classroom is the kids usually number off. I didn't say that right. She usually groups the kids together. The other one's the numbering off. Groups the kids together. So she says, okay, you 5 are in a group, and you 5 are in a group, and you 5 are in a group, and you 5 are in a group. And when she's all said and done, she realizes, hey, I have 4 groups or whatever. The second way is that she can make sure that she has a certain number of groups. And that's where people number off. I only want to have 6 groups because as one person walking around in the classroom, I can only monitor 6 conversations at once, or whatever the number is. 6 is the random number I picked. And so we go around the room and we say, we're going to number off by 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And all the 1s go to that corner, all the 2s go to this corner, and so forth. So I have made sure that I only have 6 groups. And then the undetermined quantity is how many people there are per group. Does that make sense? There are 2 different ways of organizing your groups of information. Now, these are the only 2 models, okay? These are the only 2 models. What I've drawn for you is I've drawn you set model pictures. So what you're going to see next is you're going to see an example that looks just like the ones I already did, and what's going to be different is simply how we're going to solve it. That's all, okay? We're just going to solve the problem differently. So the approach on this one to solving the problem differently is this is the missing factor model. So it looks just like the wording for the other one, okay? But it's the way we solve it that's actually different. So this is something a little bit unique that didn't happen with multiplication and subtraction that we've done before. Okay, still, Junie has 24 rocks. She wants to give them to 6 of her friends. How many rocks will each one get? So in this model, what we're going to do is we're going to set up, we talked about this with subtraction maybe, where we set up, yeah, it was with subtraction, where we set up a blank. And it looks like an equation. Well, it is an equation. It's just got a blank in it instead of, say, a variable. And we ask ourselves the question, if I turned this into a multiplication problem, what would I have to multiply by 6 to get 24? And the answer is 4. It is my missing factor. Or you could set up the equation so that it looks like this instead. 24 divided by 6 equals, and here's the question mark on the right-hand side if you like that better. Still a missing factor. Because if I change this, it becomes 24 equals 6 times the question mark. Same thing as the other one, right? And the question mark is, in fact, the same 4. And the answer here is 4 rocks. So this is more of setting it up in an equation kind of format for the missing factor one. Okay? Our last example is actually one where we will delve a little bit deeper into it when we get into section 3.5. So this is a sort of a mini version of this model, and we will make it a more massive type when we get to the later section. This is called repeated subtraction. And this is actually probably more like what Junie would do if she were doing this problem. Okay? She's got 6 friends, she's got 24 rocks. The idea is that she would go down the line and she'd give each friend a rock. And then she'd say, how many rocks do I have left? And then she'd give each friend another rock, and she'd say, how many rocks do I have left? Not how many friends. Hopefully all 6 of them are still her friends. And she'd keep going until she had no more rocks, or simply not enough rocks that they would each get an equal number. Okay? So the way that this looks in terms of a solution, like a written out solution, is that we'd start with our 24 and we'd take off 6 because she gives all 6 friends a rock, and we'd say, how many does she have left? And the answer would be 18. And then she'd go down the line and give them all each another rock, which would take away 6, and we would get 12. And we would do it again, and we'd take off 6, and we would get 6. And I'm just repeating that part of it. And we take off 6 again, and we get 0. We stop when we have less than 6. Now, obviously, we stopped because we had 0. But if we'd also had, say, a 2 left over, if we had 6, we can't take 6 more away. We'd still have to stop. And then the answer comes with, how many times did I take 6 away? Well, I took 6 away 1, 2, 3, 4 times. So the answer is 4 rocks. Let's say there had been a 2 at the end instead of a 0. What would the answer be? Still 4 rocks, but she would have 2 left over. We call that a remainder with division, right? 4 remainder 2. Contextually, it would be we would give them each 4 rocks, and we'd have 2, Junie would still have 2 rocks left over, something like that. Okay? Now, I said this before, but it's also in your notes. Note, 3 of the 4 models above do not represent different types of word problems like they did with subtraction. But they represent different ways of solving the same word problem. Okay? So I haven't had you, per se, solve the problems you've created up till now. I just had you create them, because that was the difference in our models, right? Here, the difference is in the solving, not in the creating. So, in your groups, you're going to create, basically, 2 models. That's A and B here, the set partition model and the variation for that, okay? So one where you fix the number of items in each group and one where you fix the number of groups. And then you're going to solve them by the different 4 methods once you've created those 2 problems, okay? So create a problem for A, solve it. Create a problem for B, solve it. And then use one of those problems, A or B, as the problem for C and D. Does that make sense? Okay. So when we get back together, we'll talk about the 2 problems you created for A and B, and I'll be walking around, and if you have any questions on how to solve it or anything like that, I can answer those, okay? All right, take a look. All right, we have 6 groups, which means that we can have 3 people give us 3 groups give us examples of the first type, and then 3 groups give us an example of the second type. And if we have them backwards, we'll just kindly say, I think you got the other one, right? So be all right. Okay, so part A are the ones that are going to be where we know the number of groups. So who would like to give their example of where we know the number of groups? All right, yes.
Tori has 15 pieces of bubble gum. She wants to give them to her 5 friends. How many pieces of bubble gum will each friend get?
All right, so we have 15 friends, and no, it's not right. 15 pieces of bubble gum, and we have 5 friends to give them to. Very good. So we know the number of groups that we're making out of our bubble gum. Someone else. Catherine.
Hannah made 12 cookies. She wants to divide them up between herself and her 2 brothers. How many cookies does each person get?
Okay, herself and her 2 brothers, that's 3 people. So we've got 3 groups that we're dividing our 12 cookies into. Very good. One more.
Rose has 18 colored pencils. She wants to share them with 6 of her friends. How many colored pencils would her friends get?
All right, 18 colored pencils, giving them spreading them among her 3 friends. Very good. All right, now we're going to do the other version, whereas we know the number that are in each group. Okay. Do you want to go?
Sure.
Okay.
It's Jack's birthday and he brought a package of Oreos to share with the class. There are 36 Oreos in one package. Each student will get 3 cookies. How many students are in the class?
Excellent. So we've got the package of 36, and we're dividing them into groups of 3. Nice. Ellen or Jessica?
Molly has 21 crayons. She wants to put them together by color family as groups of 3. If she groups them this way, how many color families of crayons will she have?
Nice. So we have 21 crayons, and we're grouping them in groups of 3. And then, Beth, do you want to do yours?
Sure.
Okay.
For Valentine's Day, Sally has 32 lollipops. If she buys them in groups of 4, how many friends will get a bag?
All right. So 32 lollipops in there in groups of 4. And then how many groups will she end up having to give to friends? Okay. So there are nuances, but they are different ways of talking about division. The reason I mentioned it in particular is because one of the ways of talking about it is a little bit easier to do division with when you get to fractions. So if you haven't already taken proportional and statistical reasoning, at some point you will. And we talk about dividing things by fractions, like dividing 7 by 1/2. And it's a lot easier to ask yourself how many groups of size 1/2 are in 7 instead of talking about taking 7 and making it half of a group, right? that sounds weird. What does it mean to have half of a group? It's an awkward way of thinking about it. So, all right, last part in this section is to take a look at the different potential whole number properties for division. So we're going to do like we did with subtraction. If you want to turn your desks around, that's fine. If you're good where you are, that's fine too. We're asking ourselves the question, which of these properties will hold for division? Okay, so the first one is closure. Okay, so what would that mean? It would mean if I divide two whole numbers, do I always get a whole number? No. Can you give me an example?
3 divided by 2.
No. 3 divided by 2, well, you know what, we'll write it this way, is not an element of the whole numbers. Agreed? So it's not closed. So this property does not hold. How about commutative? What would commutative look like if it held? Can you give me an example of what it should look like?
3 divided by 2 should equal 2 divided by 4.
Yeah, and I'm going to use 4 just because I don't want you to think that we have to take something that always gives us a fraction. 4 divided by 2 will not equal 2 divided by 4, right? We could actually get a whole number in one direction and not in the other direction, but there aren't any two numbers actually that when we divide them, unless it's the number with itself. I guess you could say that one, right? 5 divided by 5 works both ways, but anything else, if the two numbers are distinct, it won't work. How about associative? What would your guess be? You think it would work? Let's give it a try. I'm going to use numbers that keep this working with whole numbers so that we aren't getting into the fractional sense of anything. So we're going to take 12 divided by 4 and divide by 2. And we're going to do 12 divided by 4 divided by 2. So this is what would have to work. The 12, 4, and 2 are in the same order on both sides. It's the groups of parentheses that are different. So on the left, or the first one that I did, 12 divided by 4 is 3, and 3 divided by 2 is not so good. How about on the other one? 12 divided by 2 is, okay, it's 2, and then 4 divided by 2 is 2, and then 12 divided by 2, I said it wrong, I'm sorry, and then 12 divided by 2 is the 6. And the end all of it is that these two are not the same. 3 divided by 2 on one side is not the same as the 6 on the other side. So if we create even just one example, then it won't hold in general. So this one would be we call it a counterexample, right? Yeah. How about the identity property? If there's an identity element, what does it have to be here? 1. It would have to be 1 because 5 divided by 1, for example, it equals 5. Agreed? Okay, but there's a problem with that. What's the problem? 1 divided by 5 does not equal 5, and it has to work in either order. So in a very real sense, because this one fails to be commutative, is why it fails to be, fails to have an identity. So this is a no. The 0 property. What was the 0 property? We had it with multiplication. Anything multiplied by 0 is equal to 0. So, and it happened on either side, right? 0 times the number times 0. So in some sense, if I divide 0 by a number, what happens? It stays 0. That looks like the 0 property, but it doesn't reverse, does it? 2 divided by 0. Do you guys know what we talk about when we say 2 divided by 0? What is that? Undefined. And if you want to think about it this way, it kind of makes sense. I can't take two items and put them into 0 groups. I can't take two items and make 0 groups or groups of 0 size. It doesn't work, right? The way that we were conceptually thinking about grouping things, it doesn't make any sense. The other thing that doesn't make sense, I'm going to write it as a fraction because I kind of like that better, is if you do 2 divided by 0, it's supposed to equal some number. Let me call it x for the moment. Well, our definition of division says that must mean that 2 is equal to 0 times x. And what's the problem with that? 0 times x is always equal to 0. There is no number that I can multiply by 0 and get back to 2. That's why it's not defined. It's not a part of the definition of division. Distributive property. I'm going to show you this one too with my example because the numbers are friendly when I created them. So distribution property has to work, oh, that's supposed to be a plus sign, has to work both directions. So 20 plus 10 divided by 5. And the other side would be 20 divided by 5 plus 10 divided by 5. So I've distributed it over it. So this is one we're going to check. So we'll start with this one and see if the sides are equal. What's 20 plus 10? 30. And what is 30 divided by 5? 6. All right, what is 20 divided by 5? 4. And 10 divided by 5? And 4 plus 2 is? And that actually worked, didn't it? So we stand a chance at having the distributive property because in this direction, it worked. Now we're going to try it in the other direction. We're going to do 20 divided by 10 plus 5. So if it works, it should be the same as 20 divided by 10 plus 20 divided by 5. So what is 10 plus 5? 15. So the left-hand side is 20 divided by 15, which is a decimal or a fraction. It's 1.75. It's 1 point, that's not right. 1 1/3, 1 1/3, or 1.3 repeating. Okay, on the right-hand side, what's 20 divided by 10? 2. What's 20 divided by 5? 4, and 2 plus 4 is, yeah, it's not 1 1/3, right? Not equal. So it only worked in one direction that I gave you an example of, so that means that in general, it's another no, right? There's no distribution property. I have one last example, and this is a really common error, and it's a common error that may still even plague some of you. I answered this exact same question, but in the context of trig with my son 2 nights ago when we were doing his homework. And it looks something like this with the context here. JJ claims that the following is true by the distributive law, where A and B are whole numbers. 3 times the quantity A times B is 3 times A times 3 times B. How would you help him? What does it appear that he did? Or what did he do?
Is he multiplying the 3 twice? Because couldn't you just multiply 3 times A times B and that's still 1?
So he's doing some sort of sense of this, right? He's sort of dragging him through. Yeah, foiling. Why doesn't that work here, though?
Because multiplication, it doesn't matter what order you multiply. You just multiply straight to the 3 times A times B.
And he's using this as though what were happening inside here instead. He's acting like it's addition happening inside, right? So a couple things to think of. So I'm not going to write this down. I'm going to let you write down what it is that you'd like to write down. So one issue here is that he's trying to do something that's appropriate for a combination of multiplication and addition, multiplication and subtraction, and this problem is all multiplication. So that's sort of a conceptual error, right? Distribution is a combination of 2 operations, and this is not 2 operations. The other thing is what Catherine pointed out. When you're dealing with one operation, in particular this is multiplication, the commutative property applies, right? So the order of the multiplication doesn't matter, but you can't throw in extra numbers, which is what happens on the right-hand side of this. Everything I said is all well and good, but that may not very well explain to him why it doesn't work. Can you think of something that you could do to show him that this flat out will not work? Put numbers in. Don't be afraid to change variables to numbers to show your students that that's not a property that holds. Put some numbers in, show it. So for instance, if I let A equal 2 and B equal 4, then 3 times 2 times 4 on the left, and 3 times 2 and 3 times 4 on the right. Well, 2 times 4 is 8, and 3 times 8 is 24. On the right, 3 times 2 is 6, and 3 times 4 is 12, and 6 times 12 is 72. And these two quantities, of course, are not equal. And in fact, if you look at them, what is the factor that I could multiply 24 by to get to 72? 3. Right? If I took this number and I multiplied it by 3, I would end up with 72. Very quickly shows you I've got 3 times too much on the right-hand side compared to the left-hand side. 3 times too much. So examples are fantastic for showing this why this is happening.